So Fermi theory of beta decay. So in order to get a more accurate spectrum for beta decay, we are going to write an expression for n of p in terms of the kinetic energy of beta particles. So we know that n of p dp is equal to cp square q square into dp. So what is E square? E square is the energy of the electron. That is, we know that is P square C square plus ME square C raised to 4. That can be written as TE plus ME C square the whole square. So that is, so when we expand this term, P square C square plus ME square C raised to 4 is equal to first the A plus B the whole square A square T square plus ME square series to 4 plus 2T ME series to 4. So what is P square C square can be written as this ME square series to 4 and ME square series to 4 get cancelled. So P square C square is equal to T can be taken outside common. So T plus 2 ME C square. So what is P square? It is nothing but T into T plus 2 ME C square divided by C square. For neutrinos having momentum Q, the capital Q is given by the energy of the neutrino. We know that the rest mass energy of the neutrino, so we can write the kinetic energy of neutrino as its otherwise also the kinetic energy of the neutrino, that is QC. So the kinetic energy of the electron, that is T. Then what is Q square from this expression? Q square is equal to Q minus T the whole square by C square. So in this expression, from this expression, what is P? P is equal to 1 by C square root of this T into T plus 2 MEC square whole raised to 1 by 2. So what is dP? dP is given by 1 by C into 1 by 2. When we differentiate this, you will get 1 by 2 into square root of T into T plus 2 MEC square. And when we differentiate the term inside, this is TE square is differentiated to 2TE. Then TE into 2 MEC square is 2 MEC square into DTE. So that can be written as 1 by C into TE. These two get cancelled. TE plus MEC square divided by square root of TE into TE plus 2 ME into C square. So N of P can be written as this, all things dp dp get cancelled, so N of P can be written as T into what is P square? P square is T, actually N of P is equal to this constant, this is a constant, into P square is nothing but this T into T plus 2 MEC square divided by C square, and Q square is Q minus T the whole square divided by C square. And what is this term? This term can be written as 1 by C into this T plus 2 MEC square divided by square root of T into T plus 2 ME into C square. We are considering, we are avoiding the constants and taking the terms which are relevant for the energy spectrum. So when N of P can be written as T into T plus 2 ME C square plus. So this is square root and this will get cancelled. So the expression for N of P is square root of T into T plus 2 ME into Q minus T the whole square into T plus 2 ME C square. This is T plus 2 ME C square. This and this get cancelled. Not get cancelled. This will give the result. So N of E is given by square root of T square plus 2 ME 2 MET C square into Q minus T the whole square into T plus ME C square. So when we substitute this in this expression, that C raised to 5 is there, all are constants. The n of e t can be written as c by c raised to 5. C raised to 5 is the constant. It is the so into t square plus 2 t mec square whole raised to 1 by 2 into q minus t the whole square into t plus mec square. So that is the expression. So here also when we given the t value is equal to 0, so this function also vanishes at t is equal to 0 and t is equal to q. So this cannot explain the spectrum completely. And what is the reason for this is we are not considering the Coulombic interaction between the positron and the daughter nucleus. But because there is a Coulomb interaction, the nucleus is positively charged one. And if a beta particle is emitted, there is an attraction between the nucleus and the beta particle. That is a Coulomb interaction. We never consider this Coulomb interaction while doing this procedure. And also for positron there is a Coulombic repulsion, and we are not considering that type of potential here. So that is the one of the reason for the difference between the calculated energy spectrum and the observed energy spectrum. And Fermi uh, correct try to correct this by adding a function is known as the Fermi function, is given by f is equal to z dash p, or z is equal to f is, or f is f in f, that is a function of z dash and t, or z dash is the atomic number of the daughter nuclei. So this function has a nuclear or dependence, that is this function will take care of this Coulombic interaction between the daughter nucleus and the electron or positron, anything like that. Okay. So this is the actual energy spectrum of beta minus decay, and this is beta plus decay. Here when t is equal to 0, n of AD is not equal to 0. So at the endpoints and the spectrum and the diagram that we obtain from the above expression is not like this. This is the energy, the beta energy spectrum, because this is the energy of the beta ray, and n of number of state, n of n is a function of t. But this is the spectrum for beta plus decay. It is matching, somewhere it is matching, but not this, it is not exactly matching. So here when this function, so there is a difference from the observed value. So this is beta plus and this is beta minus spectrum. So this difference in energy spectrum is also due to the difference in the Coulombic interaction between the electron and the nucleus and the positron and the nucleus. Both interactions are different. As a result, there is a different type of spectrum for beta plus decay and beta minus decay. So this consider the effect of nuclear matrix element MFI, which we have up to now assumed that not influenced on the shape of the spectrum. This approximation is known as allowed approximation. So this approximation is known as allowed approximation, is often found to be very good for sometimes, but it is not matching in another cases. So that is MFI is vanishes in the case of if MFI vanishes in allowed approximation, giving no spectrum at all. In such a case, as we can observe spectrum, this is because of the second term in the plane wave expansion. Okay, we in plane wave expansion we consider only the first term. So when we consider the other term, there comes a certain spectra, this decay process is known as forbidden decay. As its name indicates, it's always not forbidden, but its name is forbidden decay. And allowed decay is not always possible. All allowed decays are not possible. Anyway, that we'll discuss later. So this is known as forbidden decays. Okay. So uh, so the degree to which the transition is forbidden depends on how far we must take the expansion of the plane wave to give the first forbidden decay. Then next term will give the second forbidden, and so on. So the complete beta spectrum then include three factors: the statistical factor, that is p square into q minus t the whole square. It is derived from the number of final state accessible to the emitted particle. Then second one is Fermi function f z dash p, which account the influence of nuclear Coulomb field, and the nuclear matrix element mfi the whole square, which account for the effect of particular initial and final nuclear state, and which may include an additional electron and neutrino momentum dependence s pq from forbidden term. So n of p can be written as p square is proportional to p square q minus t the whole square f into z dash p mfi the whole square into s into p into q. So this will explain the shape of beta spectrum and the energy share between the beta particle and the neutrino. So this is the Fermi theory of beta decay. So we, from this expression we get q minus t proportional to square root of n of p p square of z dash p. So the graph plotting between square root of n of p square p square f into function of z dash p against t giving a straight line. This is known as the Curie plot, or otherwise called the Fermi Curie plot. Okay. So this plot will give this is a linear nature. This plot is in linear nature, and it give confidence in the theory as it has been developed, and also give us the convenient way to determine the decay and endpoint energy or the Q value. So this is that graph. So this is the graph. This is Fermi Curie plot. So this is a straight line. Okay. So this Fermi Curie plot, this plot between this function and t will not give a straight line for uh, some spectrals. So we can make it linear by introducing a factor, that is s p q, function of p and q, against if we include s p of q in these terms against t, we will get a straight line, and s is here, s is known as the shape factor, and the s, where s is the momentum dependence, and that results from the higher order terms in the expansion of the plane wave. So when we expand the plane wave for higher terms, there comes the forbidden states, forbidden decays. Okay. So then this plot versus t will give a straight line. Okay, so we wind up this Fermi theory of beta decay here.